Oh, good morning again. Good morning, Priya. Good morning, Marina. So as usual, 7 o'clock, it's not many people. So let's wait for a few minutes until we will be more people. So good morning, Andre. Also an early bird.
Good morning. I have evening in Krasnoyarsk.
Yes, that's right. Well, afternoon at least, yeah. Yeah. So, okay, let's see. I mean, we are still the same number of people. I don't know. Yesterday, about 7:15, more people appeared, but I have to watch my time today a little bit because we have another meeting starting at 10 o'clock, and I actually have to change buildings. So I have to stop latest at 9:45. It would be better if I can stop around 9:30. So, but and we have a lot of material, and today it's let's say more in my working area. So I say good morning again, and to those who feel comfortable, it's nice if you share your cameras. So we have more a seminar feeling here. Thank you very much, Priya. And okay, with this, we start. And good morning to Moscow and good morning to Krasnoyarsk. And again, I would much rather be in Siberia now. I really love a nice winter. I know you have already snow and very different than the climate here. Okay. Good. So today's lecture, and also again, please, because I cannot observe all the time the chat. If you have any question, please just speak up. So first, I have to acknowledge here my co-authors, and Nicole Richter and Christian Thiel, Robert Eckert. They have been helping in preparing the material from various projects, but I also have to say that there is, and the references will be there. There is obviously many, many more people that contributed to the material of this presentation. Okay, what are the education objectives for today? To learn how to use SAR for biomass estimation, understand the advantages, to understand the limitations. Of course, that is important if you use a new technique, and to learn the optimal sensor and acquisition parameters for biomass estimation. There is one reading. Let's just see. This should be a longer list right now, but this is like a principal textbook if you have it available. But Henderson and Lewis, we use it a lot in our teaching because it's as an introduction to geoscientists. It's good to read, but there's obviously many other material. So the lecture is structured on starting on a definition, what is biomass, so that we all have this common understanding what we are talking about. Then the basics of biomass estimation and the estimation methods. And then we end with a couple of examples. So what is biomass? Why do we need to accurately estimate biomass locally or globally? There is a definition by the United Nations, FAO. It's one definition is defined as mass of live or dead organic matter. And obviously biomass can also include zoomass, so fauna, but we are only looking at the phytomass. And what we observe with remote sensing, obviously it is only the above ground phytomass, so we can only estimate what is below ground. And here in this lecture, we are focusing on forest biomass, not on agriculture or grassland, but similar techniques, what we are applying to forest can be applied to agriculture or grassland. But obviously here we have another dynamic. Then if we are further on the search for biomass as well, that parameter that describes best the carbon which is kept on the ground to get an estimate or to get an estimate of a parameter that is important in global carbon cycling, then we have to get an estimate of the stems, because 90% of the phytomass of forest is located in stems, 10% in branches, and 2 to 4% only to leaves. So if we get an estimate of the stem biomass, something like cubic meters per hectare or growing stock volume, what I showed yesterday, then we are close to an amount to estimating biomass. Okay. So why do we need to observe? I'm already mentioned carbon. If we can estimate the forest biomass, we have an estimate of carbon stocks and fluxes. So in a carbon cycle model, we need to have this estimate to monitor over longer times sources and sinks. And there are very famous publications using NDVI, for example, the NDVI yearly cycle since, the first NDVI data was calculated from the 70s. So we are now almost up to 50 years of monitoring on a coarser resolution and with optical data. With radar data, we have only 30 years. And as a matter of fact, yesterday I mentioned these large programs, CCI, the Climate Change Initiative. The one we are connected to is CCI Biomass. And please go to those websites. All the project products and the methods are being nicely described. And you see a lot of publications where CCI Biomass tries to come up with a standard map for today, and then they go into the past, which is always a problem because there were different sensors available 10 years ago in the radar world. There are different sensors 20 years ago or 30 years ago. So such comparisons to support global climate change are, of course, difficult. Okay, and last but not least, and this may be, of course, especially for you as participants, important to support sustainable forest resource management. You want to know how big is the growing stem volume if you are leasing forest areas to logging companies. You want to be able to estimate the regrowth possibly of forest areas, or you want to estimate emissions after a forest fire. So I see many of you obviously come from the forest sector, and so these are the terms you are interested in, I would assume. So forests cover 33% of the Earth's land surface, and obviously Russia is the leading country here on forest resources. And each year forests absorb 1/12 of the Earth's atmospheric CO2 stock. So again, forests are, and we had the COP, the meeting of the parties in Glasgow just a few weeks ago. And again, forests were in a major focus. So forest monitoring is extremely important for us, human beings on our planet. But what is even more important, that forest ecosystems account for about approximately or over 70% of the Earth's terrestrial carbon storage. So here, again, a very, very important parameter in carbon cycling. And I don't know whether you knew this or not, vegetation biomass is a larger global store of carbon than the atmosphere. And then there are, and these numbers, of course, are continuously being updated, the contribution of carbon dioxide into the atmosphere based on fossil fuel burning, an issue, I guess, that you are also all very aware of. So how do you calculate biomass? Again, there are also, actually, depending on the biome, there are different calculations, but they always include the trunk diameter, the stem diameter, and the height of the forest, so the height of a sample of trees. So this is what we try to support with remote sensing, measuring the trunk diameter, and this is where radar remote sensing plays a major role. And height, obviously, you need other measurements such as LiDAR. So what we are trying to do is to put a relation between the trunk diameter and the height, and for this we need allometric equations. So we cannot work without the forest inventory and or the local expertise. Okay, and there's one more parameter here, the tree density. That is another parameter that is often calculated using optical remote sensing, using such factors like the leaf area index, for example. And in radar, we try to do a regression directly between our mostly actually the volume scattering component, so the cross-polarized answers from the radar sensor to the tree density. And now looking at these different parameters and talking about regression, it is also obvious that we always need training. We always need a reference on the ground from which we then refer or we can calculate the biomass. What is also important, if you look at these parameters, what we so if we compare what we can measure with the remote sensing system, again, it is based on the in situ data that we receive, which is mostly the inventory. So we use the growing stem volume as our correlation parameter to get to the biomass of the forest at the end. Or we use a LiDAR system to calculate the height and then go through an allometric equation to get the biomass in the end. So to come up to a biomass of a forest tons per hectare, we always need to have some other estimates. It's not directly coming out of a radar or an optical measurement. So basics of biomass estimation from SAR compared to optical data. Why should we do that at all? It has a higher spatial coverage than optical data, especially in northern territories. This is important where you have illumination changes, or the further north you go, possibly polar night, so you do not get any data. You have a higher temporal resolution. For Sentinel, it's well, depending where you are, 12 days or often much better. The further north you go, and the further the swaths overlay. Why is it? Because, well, we are independent of clouds. So we're not only independent of illumination, but also of cloud coverage. So, and since it is a spatial estimate, it can help to extrapolate the inventory data, which is, well, usually, well, even in a small country like Germany, we have only sample points where in situ data is being taken, or we have airborne campaigns then to estimate a spatial coverage. But for example, in 50% of our forests in Germany are in private hands, and they do not undergo the federal inventory, which means for Germany to come up with emission factors for the carbon accounting, we have to have estimates from remote sensing to estimate the biomass in private forests. And I don't know the percentage in Russia of private forests versus state-owned forests, but in Germany it's about 50%. Well, remote sensing and radar, of course, but it's also true for optical. It's contactless, so we do not have to go to the areas to produce maps. And again, the retrospective analysis, the radar data, and I introduced to you the two radar sensors, ERS-1, ERS-2, starting in 1991, are available. So in 91, we did not have a full global coverage, but for example, for the Russian territory, we have what we say a wall-to-wall coverage with ERS-1 and 2 data, only starting in only for the years 1995 to 1997. Now, so for the mid-90s, you could process and you could compare your forest or produce a forest change map going back to the data from the mid-90s, well, which is already nice. Well, we have now almost the year 22, so we are also reaching for the Russian territory a 30-year history of such data acquisition. So actually, this would be almost a suggestion from me to you to go back to these archive data and do comparisons in your region of interest. And well, I already said that weather and illumination independent. So what are the limitations? What are the disadvantages of SAR? I mean, obviously, this is what we talked about yesterday, the problems of mountainous regions. Topography affects the backscatter, but I also referred yesterday to the different scattering mechanisms. So looking at volume scattering from forest, you are, let's say, for the radiometric effects, we are fortunately on a good side because volumetric scattering is not so much dependent on the local incidence angle. But we have to obviously correct for topographic distortions. This applies somewhat processing difficulties because we have to combine different images that look from different angles to the topography in areas where you have high topography. But it is not impossible. The different software programs also in SNAP, in the free ESA software, so the European Space Agency software, such programs are available. Okay, and but what is the bigger problem? So let's say this is like technical obstacles that need some processing and understanding, but they can be solved. What we cannot solve is the problem with the backscatter saturation. So especially in high biomass forests, we run into the saturation. This will be a topic today we come back to again and again. So the last sentence here that the satellite approaches to estimate biomass are still in experimental stage. This is only, let's say, partly true, especially with that program CCI, Biomass, the European Space Agency project in the framework of Climate Change Initiative. There has been operational monitoring procedures have been developed based on today's satellites. Again, today we have from the radar side Sentinel-1 as free data, operational data, but the data we would really need is longer wavelengths, L-band. So, and these are unfortunately, today they are only available commercially or as MOSA-X that I showed yesterday from the Japanese Space Agency. So that limits also our, let's say, our capabilities to develop operational procedures to estimate biomass. This will change next year when the NASA, ISRO, NISAR satellite, L-band satellite will be launched. Then we have free access to L-band data, and then all of these techniques become even more valuable, applicable, operational. So we also, this is repetition, talked about the different penetration capabilities of the radar data. We have been seeing X-band data, mostly X-band and L-band. And well, this is indicated here on this image as a, just for understanding. If you are using X-band, the short wavelength, it will backscatter from the top of the canopy. But since this is a volume, it's not a solid surface like water, you will have some penetration. And again, results show that the X-band penetrates depending on the density of the canopy up to 1 meter, maybe 2 meters. But 1 meter is like a general good estimate. So about 1 meter, the X-band would penetrate, but not much more. Which means with X-band, you cannot detect stem thickness or stem densities. What you see is the density of the canopy. So the other signal here would be an L-band. L-band with a more than 20 centimeter wavelength, 23 or even longer. It definitely penetrates the canopy. It definitely receives backscatter from the soil and interaction with the stem. Now, the next image shows what graphically what volume scattering would include, and of course it's very nice to get a better estimate of the canopy, and we can say this would be the most probable scattering mechanism for C-band, and with 5 centimeter wavelength. Again, depending on the density, C-band will penetrate more into the canopy, 3, 4, 5 meters. So you already get an interaction of the backscatter, not only with the leaves, but also with the stems. So we are getting closer to measuring what we need to measure for biomass, the trunks and the stems. Again, depending on the density, and especially, well, this is obviously more true to very dense temperate forests or maybe tropical forests, but for boreal forests, there is a very good possibility that your signal, your C-band signal, even penetrates the canopy and you have some interaction from the ground and stem. So, but C-band is really difficult. With the 5 centimeters, you cannot be that sure where the backscatter comes from. So all we can do here is, again, that's why we are using regressions. We are using correlations to inventory just to come up with a semi-empirical model which we use to then map biomass. The last scatter mechanism, so this would be single bounds, a kind of single bounds. This is a representation of volume scattering. And then we have this interesting feature called double bounds, again, which we can only experience with L-band. And it is a feature that it may also occur in certain circumstances in taiga forests. I mean, for double bounds, the two features that have to be present is you have to have twice a specular reflection. So you must have a very smooth surface. It must be, well, very smooth, or in addition, it should be moist. So that mainly you get a forward scattering effect that then the radar pulse, the next object it hits is the stem. So the stem as a water-filled column acts again as a specular reflector, and like the corner reflectors I showed to you yesterday. So this causes then again a very strong return. And what we are seeing in L-band, remember those airborne images from L-band yesterday, looking where you saw these big differences between agricultural fields and forests. This stems from a very large part from, well, interaction directly from the stems and ground and such corner reflections too. That is why we get the strong returns in L-band from forest. Now, the strongest returns come from this double bounds, so these corner reflections, and that is a phenomena that has been observed. Let's say the best area where you can see that is in the Amazon. Also, I mentioned that yesterday, is in the Amazon, where you have flood level changes of up to 12 meters. and then you have a water surface and you have trunks. Yeah, so this may, and I'm just wondering how much it could also, if you have melting snow in Russia, that could also cause a similar return here with L-band again. Yeah, a smooth, very high conducting surface where you have specular reflection and then again at the trunks. So in tropical forests, you can very nicely map the under canopy flood stage, just because you get from a state where you have just a soil beneath the canopy and you have diffuse scattering everywhere. And then when you have a flooding, the backscatter mechanism changes to corner reflection and you get very, very strong returns. So there, if you read that up for flooded forest mapping and L-band, then you find all these publications and wonderful images. Yeah, so how does a coniferous tree looks like to a radar sensor? And I really like this presentation. I use it a lot since Trudy Letuan, very estimated radar scientist with hundreds of publications. You find her on all kinds of subjects. The institute where she works in Toulouse, CESBio, there are also ecological modelers, and they have produced this graphic sketch of the major components that interact with the wavelengths. So the graph illustrates very nicely. It gives a better impression on when you're using an X-band or L-band image. What is it? What you as a radar sensor see? So again, it's always where the radar backscatter comes from is always in the dimension of the wavelength. And now you see that C-band is missing. Yeah, that wavelength that we use most, because we had the ERS1 and Envisat ASAR and Sentinel is missing. And well, there is a good reason why it's missing, because there is, excuse me, a stupid wavelength that has been decided in the 80s by oceanographers. The first European radar sensors were dedicated to oceanography. So the oceanographers decided they need the 5 centimeter. Nobody was thinking so much on land applications yet. So we are stuck now with a 5 centimeter wavelength, really for, let's say, historical, technical reasons. And there is no tree here because the 5 centimeters, it would be a mixture of needles and small branches and twigs. So here it's a leaves, small branches. It's a mixture, and depending on the density of your forest, it may even have a lot of returns from stems. And there are even scientists, if you look into soil moisture mapping, there is also a CCI project, Climate Change Initiative project, focusing on soil moisture. They're using C-band to map moisture even below forest. And why they can do it, again, it's all regression based and using multi-temporal data. So this is also the solution here with our C-band, using multi or even hypertemporal data to get a better estimate of the biomass. So, but it's always nice or interesting to see, and it just proves to you C-band is difficult. Yeah? It can come from all kinds of constituents of your tree. Okay, and you see here's even a very long, this is very high frequency. This can be several meters. These are systems that are flown experimentally on airplanes. We don't really have much results on this. This is some very small groups working on such applications. Again, from airborne data, it may be interesting. So if you are interested in this, then there's also publications on that available, but there's not much data. So I have actually never touched VHF data. but we have been using P-band, and we will see some results. Okay, don't forget that if we look at the images now. Yeah, and now I'm showing you a comparison that was produced in the late 90s, and I still love it. It's the best little set of images to explain what radar backscatter is versus radar coherence. But we come to the coherence in a few minutes. So now remember yesterday's figures where we had X-band and L-band. And here we have C-band and L-band, and this comes from ERS-1, so one of the early European radar satellites, and this comes from the Japanese JERS-1, the first Japanese L-band satellite. And we see the same problem, that with L-band we start to see differences in the forest. Here, for example, a clear cut. You can see this. Sorry, there's no scale on it, but I mean, this is from the central Siberia. So this is probably a kilometer in length here, this clear cut. But also here, probably settlements and a bit of pasture. Also here, things are coming up. What we can here clearly see is the river, also here a little tributary, and obviously some very smooth areas that cause specular reflection here in the L-band. And they are so smooth that we see them also in C-band as a black, so specularly reflecting area. Now you should already know why the river is not black in C-band. So it would be a nice exam question. Why is the river not black in C-band? Yeah, some parts of the little tributary are black, but not everywhere. Yeah, and then so if that's the question to you, then you only have to remember, okay, what are the scattering mechanisms that I know? We have specular, we have diffuse, and we have volume. Okay, so I know here from the L-band image, it is a river, it's causing specular to L-band. Since it is a river, it cannot be volume scattering. So the only solution answer is it's diffuse scattering. And why is it diffuse? Because here the river is wide enough, obviously through wind or currents in the river, the surface roughness is with respect to C-band, to the 5 centimeter. Yeah, it is a roughness that causes already diffuse scattering and not specular reflection, like here for the longer 20 centimeters. The roughness must be much higher to cause a diffuse scattering, and diffuse scattering causes higher reflectances or higher backscatter. And that's why the river is whitish, bright in the C-band, and it's black in the L-band. And this is also the C-band, the 5 centimeter is a wavelength that is like the right size for such water surface roughnesses. That's why the oceanographers choose that wavelength and like the wavelength very much. Okay, but for us, if we would map this, if we would try to map something automatically here, this results in a problem because we could not discriminate river from forests even. So again, here are some very smooth areas that cause also for the C-band specular, but everything else is diffuse or in the forest volume. Now let's look at this piece here and then this one. Now they're almost not visible in the C-band. Almost not visible in this single C-band image. And that is what is so frustrating to many people from using optical data. I say, well, I mean, I can't see a difference. The difference will come up when you look into coherence and when you look into time series, but a single image is really useless. And even a few C-band images may be used. So why is this? Well, on this log territory, as you know, there's either already regrowth, so there's small bushes or small trees, or the remainders from the logging, the debris, wood stems, now the branches, whatever is there. So actually the area is not really smooth for a C-band. So it causes backscatter either because it's a rough surface from the debris after logging, or there's already regrowth. And then for the C-band, remember, it penetrates the canopy. So if there is already some bushes, that doesn't make a difference for the C-band whether it's a tree or a bush, because it's just volume scattering from the vegetation that is there. That makes it so difficult to discriminate from C-band backscatter the forest from a bush. And again, I show this image, I like to show this because it teaches you to look at the images like you have radar eyes. What is the size of the scatterer? What's the wavelength I'm using? C-band 5 centimeter. What is the size of the scatterers from where the backscattering comes? Okay, but the L-band is helpful, and of course, the forest is gone, so there is no volume scattering for a long wavelength like 20 centimeters. And so there is so first of all, there is no volume scattering, but there is also more scattering away. I don't want to really use the term specular because it's not as smooth as a water surface. Yeah, but there's not much left in the size of the wavelength that gives backscatter. So L-band, even a single L-band image is nicely to use to map forest, non-forest. If you're interested in just mapping where logging or where fire has happened. And of course, radar looks through fire plumes. So you could also, while a fire is burning, you can observe. That is, of course, very nice. Yeah, with optical data, you cannot look through the fire clouds, the dust, the aerosol plumes. With radar, you can. So you would have an instrument, the Sentinel-1, for example, to map. Sentinel-1 is C-band, but you have the time series, which help you then to discriminate between forest and non-forest. So, but L-band is, of course, much better. Okay, yeah, and even here, these areas which may be really just agricultural fields or pasture, here we see some bright returns, maybe a little village. Yeah, these are almost not visible again. Yeah, with lots of fantasy, you can say, okay, yeah, I know there's something, so there must be something there, but you don't really see it. Yeah, but now look at the coherence. Now the coherence looks like a mask, like a black and white mask of forest and non-forest, but this needs some explanations. Okay, we also look at the river. It's black again. We look at these smooth areas here, and they are bright. Yeah, they're the brightest returns. We can very nicely see here. Unfortunately, this sits on top of this piece, but we see this piece here. Yeah, and then there were here these two small ones, almost not visible even in L-band, but they suddenly show up in the coherence. And also we see very nicely these valley floors and the difference between forest and non-forest. Okay, so what is this coherence now? And that is I think it's so surprising. This coherence comes from an interferometric process using, and this is now the big surprise, using two C-band images. And so the coherence contains information that is not visible in the backscatter. And this is another lesson from these three little images here. The lesson is that coherence, this interferometric product, and I will tell you how you produce this, the interferometric product gives another surface information than the backscatter. It is not to 100%, but almost to 100% independent information. So what is the coherence? Coherence is a correlation coefficient. It's the correlation of the two phase images. And well, we had the difficult lectures yesterday and the day before. What is phase? Yeah, it's the state of your radar wave, whether it's a peak or the minimum of your amplitude. And since we're using coherent radiation, we know the phase condition of the pulses that are being sent out, and we also measure the phase when the radar returns are coming back. That is why we have a complex number, or radar data is stored as complex numbers containing the amplitude. This would be this image. the intensity of the backscatter, and the phase. Now, the phase of a single image, I will show you also later, the phase image, one single phase image, doesn't give you any much information because it's just a repetition of this phase condition. It gives you really no information. But comparing two phase images, what we see now in the coherence, and comparing really means producing the correlation coefficients, of correlating the two phases, we see in the coherence map where the phases match nicely between these two images. And obviously, this is the case in these areas. They match 100%, maybe 100%, very high correlation coefficient, very bright. So they do not match over the river. And they match again nicely in the deforested areas. And they do not match in the forested areas. So the value range for coherence, since it is a correlation coefficient, is actually between 0 and 1 as a correlation coefficient. So these areas would have values around 1. These would have on the river around 0. And here, well, maybe values of 0.3, 0.4, and in these unforested areas, 0.7, 0.8. Okay. So, well, some of you may know this already, but for those who never heard about this, you have to digest that information now a little bit. Yeah, so it's the correlation coefficient of the two phase images. And in this matter of fact, actually, well, this is, you see one image and we need a second one. And then we calculate the correlation coefficient of the phase. Now, what does this mean, this difference of very bright and dark? What this means is this surface is smooth. We know that from our backscatter images, it's smooth. Specular reflection here, specular reflection even for C-band. Yeah, but to have such a high correlation coefficient means that on the surface, nothing has changed between image 1 and image 2. Nothing has changed on the surface because the phase of image 1 is exactly the same as the phase return from the image 2. They match perfectly. Yeah, so nothing has changed on the surface. Now the river is the opposite. Yeah, the little current on top. Of course, they are on a different location on day 2 or acquisition 2 than on acquisition 1. So we are losing completely the correlation. The phase is completely different at the second day versus the first day. Yeah, and well, that there is a roughness we see here. Well, this is C-band coherence. I should put this in front. It's not L-band coherence. It's a coherence of two C-band images. Now we know from the backscatter, okay, there is a rough surface. It's diffuse scattering. Yeah, and obviously the rough surface is different on day 1 than day 2. So this is why we lose this the correlation totally, completely. So to interpret now what this is, yeah, this is obviously, this must be very flat surfaces, possibly agricultural surfaces, and yeah, either there is standing water in them or they are very smooth. Maybe they are plowed, they are very smooth. And we see here the backscatter, you know, it's not for C-band, the 3 centimeters is not everywhere really smooth. There's some roughness on top. But what we know is the surface is stable. So what I just said, well, some water on the surface can actually not be true, because even in the areas where we get some backscatter here, because of diffuse scattering, this must be a rougher surface with respect to C-band. It's smooth with respect to L-band, but it is not moving. It's not moving. Otherwise, we would lose the correlation here. Yeah, which means, okay, it's not standing water, it's just this very flat surface. It must be very smooth, very flat and smooth, because the C-band also has specular reflection in these areas. So most probably in agricultural fields, just plowed, but in a very smooth. Okay, but now the interesting, most interesting result of this is one of the very first coherence images ever being produced from forests in the mid-90s. And it was more experimental to see, okay, what information content is in a coherence of two C-band images. And well, everybody involved was really surprised how clear the difference becomes between forest and non-forest. But with further research and after, let's say, what's the time now? Just continue. Okay, we finished it then. With further research, we also found that the coherence is actually sensitive to different biomass contents or to different growing stock volumes in the forest. But again, it's puzzling. It's really puzzling that on the individual backscatter image, you see not much difference. And when you now not look at the backscatter, but you look at the phase information of two such C-band images, you get a wonderful forest, non-forest mask, and even more information on the biomass. There you see the deforested areas clearer than even on the L-band. So, and this is what I think is really the power of radar, that now the phase information is so related to the structure of the backscatterer. So now let me just go back here because this is so nice. Okay, we are looking at C-band, and obviously C-band 5 centimeter goes more into the branches. But what this coherence image of two C-band or coherence map of two C-band images shows is that looking at the phase differences now, it's almost an indication of the type of scattering geometry, because it is so sensitive, the phase is so sensitive to where that scatterer is on day 1 and day 2, or acquisition 1 and acquisition 2. So the more volume you have, the more scatterers you have of the size of your C-band image, the more you have decorrelation between your phase information of acquisition 1 versus 2. Now, and it is a bit hard to digest, but just think of it really physically. It's the amount of scatterers of needles or leaves in the size of the C-band and of little twigs and branches of the size of the C-band. And the more of such scatterers you have, the more possibility that with a little wind, where there's always wind, they are not at the same place between day 1 and day 2. Now they change a little bit in space, and this causes the decrease of the correlation between the phases. So it's very sensitive. Now the backscatter is something else. It's the more water you have, the higher is your backscatter. So the backscatter information is related again to the volume, how much water is there, but it's very closely related to the amount of water. So the coherence gives you information about the geometry and the intensity. The backscatter intensity gives you information about the water content. Okay, very, very powerful, but you need now to know what is interferometric processing, what are the conditions to produce such coherence maps, and I can only tell you now with Sentinel-1, again, we have many projects in South Africa. We are focusing really on the power of coherence, looking into coherence time series. And I'm absolutely certain that looking into coherence time series over Russian forest territories, you are able to come up with excellent models describing your biomass and biomass changes, even subtle changes, or regrowth, monitoring regrowth. And with Sentinel-1, you have a workhorse in space that gives you, well, at least every 12 days, but depending where you are, it's probably, I haven't calculated it, but looking at the overlapping swaths, it may be every 3, 4, 5 days you can come up with such an interferometric pair to produce the coherence. Very powerful technique. Okay, and this is showing you now, and then we do a little break, the ERS tandem. Okay, there's a new term, tandem. ERS were these first satellites of the European Space Agency, ERS 1 and 2. And there were some times it was called the tandem mission when these two satellites were programmed so that exactly 24 hours were between acquisition number 1 of ERS 1 and acquisition number 2 from ERS 2. So we knew exactly, okay, there are 24 hours exactly between the two acquisitions. And this is shown here, a 1-day repeat pass. So here comes the word term phase, coherence image. And this is even, I think, over some tropical areas. And again, you see backscatter, coherence, backscatter, coherence. Very, very powerful. Yeah, you see things you didn't see. Oh yeah, and this is a nice example. JEIS, that is that L-band image that I showed you. That's a satellite from the mid-90s. Now, again, it's the same area. Let's just look here on the left side, C-band, L-band, C-band, L-band, C-band, L-band. And in the L-band, as in the Siberian example, with the L-band backscatter, you already see differences, deforestation. Okay, and now what is this on the right side? Here it says a 44-day repeat pass phase coherence image. JEIS was a lonely satellite. It was only one satellite. So to produce an interferometric pair, we had to wait 44 days until the satellite comes back again, the repetition frequency. You know, like for Landsat, what was it, 18 days, I think. Yeah, so until, again, the satellite has done its global coverage and it's back on the same location. And for JEIS, this was an orbit that had a 44-day repeat. So here we did not have that nice 1 day, only 24 hours. Here we have 44 days, but still the L-band, being much more sensitive to the tree trunks now, even as 44 days in between, shows also better the deforestation than the backscatter image. Yeah, also here with L-band. So, and with the long wavelength, you can go to longer, we call this longer temporal baselines, longer temporal differences. And since obviously the tree trunks don't move between 44 days, they even don't move between a year, then you get still a nice coherence image because your scatterers are stable. Okay. Oh yeah, this is even now 100, oops, what did I do? Yeah, this is now 132 days, so almost 4 months after the first acquisition. Yeah, and if you just look at the right image, your speckle increases, but the information of the coherence still stays. Just because, why? Why? We'll go back. Why? Because L-band scatters from the trunks, and the trunks, of course, do not move much, as I just said, between acquisitions. You can even take acquisitions of years apart, and you would still see a nice coherence image. But of course, here in the speckle also increases. Okay, so with the next lecture, but just after a very short break, just 9 minutes. Let's be back, please, at 10 past. We continue. Any questions at this point? No, and there's also Yakimov. Thanks, Yakimov, for turning on your camera. Anybody else? Well, when I come back, it would be nice to see some faces. Thank you. Okay, so welcome back. And again, yeah, if you feel comfortable, it's nice to see some faces, and perhaps you want to turn off on your camera so you see each other also, and you get a more seminar feeling. And I can only repeat, I would much rather be in Moscow or in Krasnoyarsk now at your nice locations, and I miss Russia a lot. So, but hopefully we get there. And again, I would like to repeat that if you are interested to work with us, we can always, there is funding available through different, especially the German Academic Exchange Service, for example, but also through internships. Just let us know. And well, perhaps I hope we can also find some other ways of cooperation again in projects. So just contact me. And I have today to be switch to another building later, so I need to stop at 9:30 would be good. So and let me just check how many slides I have, because maybe we will not have another break. So a lot of stuff, and usually I get carried away, and this is I can't see it right now. Okay, but I have to speed on a little bit here. Okay, so we talked. Yeah, excuse me, and I speed on a little bit, but there's a lot of things we talked. I talked so much about the last 2 days. We don't have to repeat this. It's all obvious. Now, coherence is new. And here's a reference to another module of our EO college. Yeah, so again, yeah, within this short week, we cannot do everything, but there is a lot, thousands of slides available on the EO college webpage. Here, for example, also into SAR interferometry. Some basics we will discuss here, and also tomorrow, I think, is a lecture on interferometry. But obviously, there's more to learn or to repeat, and more references. If you're interested, please follow up these remarks. Okay, one term I use now, a new term for you, temporal baseline. Yeah, the baseline, that's a term that defines the difference between these two acquisitions, acquisition 1 and 2. For interferometry, you always need 2. It's like stereoscopy in the optical. Interferometry is the kind of analogy in radar. That's always need 2. And either you have a spatial baseline, that is the distance of these 2 satellites, or a temporal baseline, that's the time 1 and time 2 between the 2 satellites. So baseline defines that difference. And okay, well, interferometry, well, coherence analysis is one that I've just shown to you. It's based on the phase, but the phase is also used for elevation model creation or differential interferometry, where you look into very subtle changes of the lens surface. Well, then polarimetry, that is a topic we will not cover here because it's not operationally available. Yeah? There's airborne polarimetry. There are some scientific data takes from the Japanese ELOS Pulsar, also from the German Terrasa Tandem X. They have polarimetry capabilities. Now, what does it mean? It means that you're not only acquiring data in the one copolarization and the dependent cross, for example, C-band VV and C-band VH. So you send out vertically and you receive the vertical component and the horizontal. Or the Japanese had L-band HH over many years. So you send out H horizontal polarized and receive the horizontal polarized, or HV, because we are sending out H, you're not changing that, but you collect the vertically depolarized plane. And the polarimetric system does all. they change quickly between HH and VV, and so they collect also the cross polarization HV and VH. So it's a full polarimetric matrix. The two copoles, HH, VV, and the two cross polarizations, HV and VH. So, but again, these are experimental data takes, so not really for operational mapping, except you pay for it. That's why it's not covered here, and because of time, obviously. And then this gets really crazy. PolInSAR is a technique, polarimetric interferometry, now looking also into polarimetric aspects of these phase differences. So again, this is done from airborne, mostly more airborne data. There's also lots of publications on it, and the experts on polarimetric interferometry obviously hope that one day there will be a satellite available enabling that as well. And that may, of course, happen, but it's not content here. But so there's more crazy things on the way. And then there's something called SAR tomography, like brain tomography, SAR tomography. And also this implies PolInSAR techniques, polarimetric interferometric SAR techniques, and we're not covering that here. So, but there's more if you really get hooked on radar techniques. Okay, the estimation methods. Just go quickly through the whole thing. So one is regression methods, as I said before, relating the backscatter or relating the coherence to above ground biomass, so to something that has been sampled on the ground. That is usually done. Another way would be to develop physical backscatter models. Such models exist. There's a very famous one, MIMICS, Michigan microwave canopy scattering model MIMICS. But practically, it turned out that if you really want to do it carefully, you would have to model each backscatter from each leaf and twig. And so the work was, after a few years, to what I know, it was stopped. And then again and again, I tried to revive this activity, and perhaps there's now a chance using new techniques like machine learning, perhaps even artificial intelligence, to get to. The idea would be to have like an unsupervised learning algorithm which has parts of a physical model. But to include these parts of a physical backscatter model, you still need to train and to understand very well which wavelengths, what are the environmental conditions, and what's the forest structure. So this is a very interesting new direction, but it's really only developing now. It'll bring, because we have the Sentinel-1 wonderful time series and wonderful coherence time series, we can start in this direction. Maybe it's also of interest for you. Now, what's the other one? Conversion from forest parameters. Here, a conversion through allometric height biomass relations. So we would measure the forest height, for example, but for this, to get forest height from radar, you would need polarimetry and interferometry, and it depends on the wavelength, but because with X-band, there is also there are height maps, forest height maps available without using polarimetry, only interferometry. But again, with X-band, where we know the backscatter comes from the top of the canopy. But it is inaccurate, as I said before, because we have penetration, a meter or maybe a little bit more, depending on the density of the forest. Okay, so focus on, for us is here the regression techniques using backscatter and or coherence. Now this graph, and there comes many more of this type, shows the problem that we have in radar remote sensing. This is again, here we have Truilet Wan, the famous radar scientist. She has collected lots of data and compared here different test sites, France, Sweden, Colombia, etc., with high above ground biomass amounts, up to 280 tons per hectare. And here we look at a p-band, so the over 70 centimeter and cross-polarized HV backscatter. We talked about what dB is yesterday. Here you see these negative numbers. You know now why they are negative. And what you see is that this regression between the in situ measurements and just the backscatter, there is an area where it's nice. Let's see, you're starting at 20, 30 tons, and it's almost linear, but then it curves. It's an exponential function, which we say saturates then at a certain point, meaning, well, maybe here 150, 200 tons per hectare, you would not be able to discriminate that anymore with an increase of backscatter. And so what is hidden in this is this relation between the volume scattering of our backscatter and, of course, the density and the amount and the thickness of the trunks. So, let's say the longer the wavelength, you would hope that you get more and more interaction between trunks and ground and trunks and big branches. So your backscatter relates to this biomass term. And the shorter the wavelength is, then for that backscatter, for that volumetric, it's volumetric backscatter, oops, sorry. For this volumetric backscatter, it cannot detect more than it already detects being stuck somewhere in the canopy. So this is what is causing this saturation. There is not more backscatter possible because of the length of the wavelength coming from a layer in the canopy where it just, that's the volumetric scattering it gets. There's nothing more coming. So the trend towards this longer wavelength is specifically to try to resolve this saturation problem, and to have longer wavelengths, especially to map biomass in the tropical forests, not so much in the boreal, rather tropical. Okay, so these are, again, this is experimental results from test sites, and here again, please notice, if you want to look at volumetric scattering, you can just use this cross-polarized term, whether it's HV or VH doesn't matter, because it's volumetric scattering, HV or VH. So if you have a nice L-band image from the Japanese satellites, or next year from the NASA, NISAR satellite, look into HV and look in your biomass regressions, and you will get exactly the similar curves with a similar problem. But there are ways to get out of this saturation problem. Okay, this is just a similar thing here from SAR data, comparing it to LiDAR above ground biomass. You always see this kind of curve, and then a point cloud, a clump of data sitting here. And this is even a comparison of CHH, LHH, P-band HH, and so that this saturation point, it's here at 15 tons per hectare. Here it moves a little bit up, and with the P-band, we think it's getting a bit better. Then with the VV, a similar behavior, but actually less backscattering niveaus. And here with HV, because of volumetric, you get nicer returns. But the message here of these 9 little diagrams is with the P-band HV, this looks like an optimal wavelength and polarization to get almost linear, not really, but more linear regression, more sensitivity to the above ground biomass. Okay, so we talked about this intensity. So I rush a bit, but you have the slides, so you can look this up. It's a lot of repetition. The saturation level depends on the wavelength, it depends on the polarization, and of course on the object characteristics and the ground conditions. So that is something that is actually very helpful in Russia, because during frozen conditions, your scatterers, your trees, first, they are more stable than in summer. And what is more important, with your very low temperatures, the water in your trees, if there is any left, and it's frozen. So the water is in a crystalline structure, and the radar waves, like in your microwave at home, in your kitchen, when you put a frozen chicken in your microwave, it gets warm because the microwave, usually C-band or S-band, you can check at home, it penetrates that material, and wherever it hits a free water molecule, it brings the water into rotation, and that heats up your tissue of the chicken. So, and the same is with the forest in Russia in winter. If they are frozen, the radar wave, because the water is in a crystalline structure, it penetrates better through the forest canopy or the frozen trunks. And this relation between coherence and biomass gets much better in winter. So you want to use winter images of your radar data when you're using coherence as an estimate. And so your country is perfect for that. But yeah, and available time series. And we are now in heaven. We are in radar heaven with Sentinel-1A and B and wonderful hypertemporal time series. But let's say heaven could still be improved because it's only C-band, L-band would be much better. So that is why yesterday we ended up with an outlook on radar images. And what we are all really, really wishing for is a something like a tandem L mission. Yeah? So we need 2 satellites in space to get a nice small temporal baseline between the 2 satellites. That would be the solution for many, many monitoring problems. Okay, and we will get there one day. Okay, the saturation problem, there's a very famous model, the water cloud model, and as you see, it refers to the vegetation model as a water cloud, it's just a canopy full of water molecules. And the assumption is that the relation between the radar backscatter intensity and the above ground biomass this is a mixture of how many water molecules, how thick that water cloud is on the ground. So what we want to understand, if we want to develop a regression model, what is the backscatter from the ground and what is the backscatter from the canopy? How is that relation, backscatter of ground versus the amount of biomass? And okay, there's one more thing I want to, before I forget it. Yeah. There's also one that should not confuse you when you're working with the radar data. I mean, obviously, you see here the spread of your data, the variance of your data is getting much bigger if you go to lower biomass. And I mean, obviously, it's just to remember what is happening here is that is, of course, the influence now of the backscatter from the ground, especially with P-band looking through the canopy, but also with L-band. So always your spread of data will be larger, also using Sentinel. When you go to low biomass, because here you have the direct influence of the underlying ground. Just to not be confused in what's happening here. It's the ground effects. And this is, of course, that is why ground becomes here important in this water cloud model. So what this water cloud model tries, I introduced sigma naught yesterday. It says that the measurement we get, the backscatter value that we get in our radar image, the sigma forest, that has something to do with the backscatter from the ground. So kind of 1 minus whatever density the canopy cover is, so backscatter from the ground, plus the backscatter from the ground times the tree transmissivity, so estimates on the signal attenuation because of the tree height or tree density. So these are all terms we have to estimate. Yeah, we don't know them. So I can only refer you here also, please, if you're interested in this, look into the CCI biomass documentation. It's all online available. because there you see how smartly the team puts together estimates about the tree density, transmissivity from other terms, for example, an optical LAI product, or you would also have forest maps. You have estimates on this, so that you can include here to better estimate the tree transmissivity, and all of this to get a better relation of your backscatter intensity to above ground biomass or growing stem volume, if you're using forest inventory terms. Okay, and then we have, of course, the backscatter we see in the pixel, our dB number, is a mixture of ground, and this tree transmissivity term, and a mixture of what we really want to see, the backscatter from the vegetation. So it's a very simple assumption, but now how we train it. So we need to know what is the backscatter of the ground and what is the backscatter of full vegetation. Here's a similar thing, but now we have the transmissivity term here in an exponential function. So these are now the three unknowns. What is the sigma naught from vegetation? What's the sigma naught what's the forest transmissivity coefficient? And what's the sigma naught from the ground? But this can be trained now if we have the respective in situ data. And that is what has been done then on various projects. Of course, this assumption is based, and this is just another graph of the C-band, L-band, P-band old publication. They're showing also differences between Coniferous and broadleaf in the absolute level of the backscatter, which is, as you can see here, it's actually minor. Maybe in P-band a little bit is coming up. But oh yeah, it's just general radar knowledge, let's say, but some of you are beginners, so just that you see the HV term, this is the little triangles, the HV term is always lower than your copolarized returns, HH or VV. Because they're looking at the cross-pol, HV or VH, doesn't matter. What it means is you send out in one plane, and what you receive is the depolarized wave plane. So it's natural that if you turn your observation plane, that you receive less signals than staying in the same polarization plane that you have sent out the signals. I hope that's understandable. So yeah, don't be surprised that your HV or VH is lower than your copol. That's natural, and this is happening in all frequencies. So in C-band, L-band is what you would mainly use, possibly not P-band yet. Yeah, this is all was airborne SAR system. You find many publications based on this airborne system already doing research in these different frequencies. And what you see here, the angles, 40 to 50 degrees, is maybe another good advice. Yeah, it's better to use mid-range angles or far-range angles, but with far-range you may get into trouble with shadow, but try to avoid the very steep angles if you have topography, because then you get into these layover effects that are not so nice. And plus, yeah, the larger your incidence angle, the longer the way of your radar wave through the canopy, and that's what you want. Yeah, if you look steep, then you get almost always, even with C-band, an interaction from the ground, which you don't want. So try to look, because you can actually determine with Sentinel-1 also what kind of incidence angles you may want, or you choose your orbit in a way that your test site is more always in the mid or far range. Interesting. Okay, because again, just think physically. Yeah, the way of the radar is longer through the canopy. These were all monotemporal acquisitions, so things change very much if you get into multi-temporal. Okay. Yeah, and this is again and again different publication. It's an all known problem. Again, we have here HH, VV. biomass tons per hectare. And there's also something funny happening if you go to very high. Well, I'm not going into this. This is some speculation here. No, it's just this is again the same thing. Okay. Yeah, some of our own work here. You have seen the image before of a Japanese L-band image, where we've seen nicely, also in Siberia, nicely the difference between forest and non-forest. And now, if you add multi-temporal data, so this is now 9 L-band images, you get at least only looking, this was for Siberian forests, up to 250 cubic meters per hectare. This was the inventory data. There you get, except here for an outlier, you get all the linear relationship. Very nice. This was the retrieved stem volume from that water cloud model and the ground truth. Now, outliers like this, of course, can happen because there is a discrepancy between your in situ data and your radar data. And let me allow to say, I wanted to say radar data don't lie. Well, obviously, no remote sensing data lies. I have a motto here in Jena that I teach my students. And the motto is treat each pixel with respect. Treat each pixel with respect. Because each pixel is a physical measurement. And you really have to honor that. Each pixel is a physical measurement in the wavelength that you are using at the time that the measurement was taken, and obviously geometric resolution. But looking at those images, we sometimes forget that each pixel is that physical measurement, and it's not lying to you. So if the pixel is not behaving the way you want it, then you have to change something in your thinking and your mind. And where you want to get at. So I'm really a big fan of data exploration, because that's why we do remote sensing, to discover things. So that's why I'm saying, if we have such a regression as a student, you sometimes think, now I take this out, this is not helpful. No, this is a real measurement, and there is a reason why that pixel sits, or that site sits somewhere else. So possibly because it has been locked, or there was fire or something. That's why you need many samples to get to such regressions, and then you can explain what the outliers are. So just a little excursion. Okay, summary, we said that saturation, we talked about it, depends on forest type. We saw that as well. There is saturation levels where we get it when we have singular acquisitions. Combination of wavelengths is better, because then we see different aspects. This is again more summaries. I think I said all that stuff, and you can read it. You don't have to read this now. We want to go to further examples. Here's again the reference to the interferometry. Now, what is interferometry? And we come back to that tomorrow again. Okay, don't get too scared about this little calculation here. Why I'm showing that is only to show you again, coherence is a correlation coefficient. So, but these funny numbers here, these stem from the complex image values. Remember yesterday we looked at these graphs, looking at how speckle was generated. So having intensity and phase kind of included into that complex number. So this is why they appear here, but other than that, it's the formula is exactly like the correlation coefficient. Here you have your average, and then it's divided by the squared sum of the variances. Okay, so in this term here, gamma, so we learned sigma naught as the calibrated radar backscatter, so the intensity. And gamma is the term for the degree of coherence as an absolute value. Now we only want 0 to 1 as a value range. That's the degree of correlation. Now, correlation of what? Correlation between the phase information of acquisition 1 and acquisition 2. And here we have the B for the baseline. It's a geometric term, the baseline, because the satellites can have different baselines depending on their orbits, and that influences the coherence. Or it's this temporal baseline, which just says, okay, this was on day 1 and this on day 2, or the examples from JERS, day 1 and day 44, or day 1 and day 144. Yeah, so the temporal difference. So we have to know when was the acquisition. Okay. Yeah, interferometric coherence is reduced by temporal decorrelation. The longer the time between the acquisitions, the coherence goes down. Geometric decorrelation, if there is, let's see here, if the baseline is too long or too small, then we also run into trouble. So nowadays, when you want to produce an interferometric product like coherence or an elevation model, then, for example, for these old ERS 1 and 2 acquisitions from the 90s, if you order them, you can also ask for the baseline. Now, what was the distance between the two satellites? And then you get the information, and there's also explanations. What is the optimal baseline? And I think it's somewhere for ERS for C-band is somewhere around 100, 200 meters, about that range. So if it gets too large, to 700, 800 meters, then you're losing the capability here to produce a nice coherence map. So that is why geometric decorrelation is listed here. The baseline is important. Then, of course, yes, now atmosphere starts to play a role, because we're not looking at the backscatter intensity. That's easy. Yeah, but we are looking at the phase condition of that pulse, so at the returning phase. And if you have, for example, at acquisition 1, you have a thick cloud here in the middle between where the wave has to penetrate 2 ways, down to the Earth and back. Now then a thick cloud with lots of water droplets in it will not change your amplitude much, not the intensity, but it can have effects on the phase. But that really depends on how thick that cloud is. So, but you will see that if you produce a coherence map, you may suddenly see areas that look kind of blurry. They look different than the surroundings, but it's just by the shape, you would see that this is an atmospheric effect. Now, so I have been talking radars independent from atmosphere. Yes, if you look at the amplitude, at the intensities, but looking into interferometry, this may be an effect. It's just something to remember when you have strange, noise like speckle. There is, of course, a sensor inherent things, but they are everywhere anyways. Okay, there's really not much new information. Yeah, this is a, what was this? There's a decorrelation. Okay, this is important. Just see, I need another image here. This comes later or tomorrow. Okay. Because I'm not sure whether you have all already seen such interferograms. Yeah, this is an interferogram, and it's showing you the interferences of 2 radar images. And here we have our good old gamma, and you see here a gamma of 0.3, 0.5, 0.6, 0.8. So, in the higher the coherence, the correlation between the 2 phases, the better visible, the clearer, the more distinct becomes this interferogram. Now, what is the interferogram? So in the early times of interferometry, and it started already in the 80s, there were first airborne experiments showing that, wow, yeah, with 2 phase images, we can produce an interferogram. We can produce an image that shows, and these things have an artificial name, they're called fringes. we can produce an interference pattern, and we call them fringes. It's a new word, because this is not otherwise not existing. Except we correlate to phase images. Now then we see these interferences. So what is this? Again, an analogy. You are at a lake, and a smooth lake, and you throw two stones in that lake. So the stones are like the radar antennas. They are emitting now a frequency that is causing little waves around them. And when these waves meet, now then you have sometimes the amplitudes add to each other. So you have a constructive interference, or they subtract each other, and so it's a destructive interference. But there will be a new pattern arising of interferences. So, and this is exactly what is being done with interferometry. It's the same thing. Your radar antenna is emitting wavefronts, and there is a second, and it doesn't matter that it's not at the same time, but it's on a different time, a day later, emitting again wavefronts. And since we receive that phase information, we can compare these two wavefronts, like the two stones in the water, and you see an interference pattern. So in this interference pattern here is, of course, you see it, the better, the nicer, the more distinct, the better these phases match each other. Now, when they match nicely, then you see that those interferences, and let us call them from now on fringes, you see the fringes much more clearly. So this coherence estimate was only used in the beginnings of interferometry to show or to prove that the fringes are visibly good enough to produce an elevation model. Now, the original reason to go into interferometry was to produce elevation models, not to use coherence like we use it now for surface analysis. Coherence was only introduced as a correlation coefficient. Let's see how well the phases match. And if they have a nice gamma of 0.8 or maybe 0.6, there we can develop an elevation model. Now, what is happening here, these would be an interferogram or a fringe pattern of a forested area, for example. As we have seen before, in the forested area, the coherence was very dark, very low, probably around 0.3. So if the coherence is low, then also my pattern, my fringe pattern, is not very well visible. So there was a margin in the 90s around, I think, gamma 0.4, something like that, where it was said, okay, now from this kind of fringes, you cannot develop an elevation model, because each of these fringes will later become an isohypse, a height line. And each difference between these fringes is an equidistance. So between, let's say, for TerraSAR tandem X, I think it is 10 meters, or is it 1 meter now? I think it's by 1 meter. Okay, and that pattern here arises because, obviously, this interference pattern comes from a repetition of my wave. So what you see is the repetition of my wave being formed as, well, either 360 degrees when you think of a circle, or 2 pi. They're going through the amplitude peak and then the minimum, and then starting again with the next wave. So it's always a multiple of waves. That's why here it's just a multiple repetition of this type of pseudo-colors. Yeah, but you will learn more about this. Today we talk about the applications. Okay, yeah, so this is similar what we've seen before, a one-day ERS C-band tandem result. And here we did the same thing, but looking just at repeat paths of that ERS, one satellite when it comes back 35 days later. For JERS, it was 44 days. So here you see now the resulting coherence of these two different images. Yeah, if you're only 1 day apart, so the highest coherence, if you're looking up here, comes from fields and from urban areas, because they don't change within 1 day. What is changing is the forest, because the leaves are on a different position. The little wind already is enough to have the leaf on a different place. So the coherence goes down. And of course, here, water is here very unstable because obviously it moves. It's not at the little surface roughness is not at the same place. So with an image like this, you can already do a nice little separation. Yeah, we would have problems here between urban and fields. For this, you would go into a longer temporal baseline, because then everything has changed except the urban areas. Yeah, if you look 35 days later, your fields, yeah, the surfaces have changed. What else? The water anyways, the forest is still very low coherence. But the urban areas will stay relatively stable, and they will be distinguishable. As you see here, the bright spots are all urban areas. So it's the same area as here above. So it's, and this technique is being used also to map urban developments globally, to monitor changes, because, well, if only in coherence you can discriminate them easily as like a mask. And what this shows is urban scatterers are so stable that we can monitor them over years and years, and that's the basis of the so-called differential interferometry, where you observe a certain point in that village exactly over years, and this is the basis to map surface changes of millimeter variations. A technique done all over the world now. In Germany, for example, you can find a web page that gives you a map of Germany with all these, we call this the persistent scatterers. It's a persistent scatterer interferometry. And so there is a map of these persistent scatterers, places on our German territory that are stable, and they are being used by our geological service from Germany to monitor surface changes that can happen due to tectonics, they can happen due to mining below ground, can happen due to infrastructure, such things. And so the accuracy is now in a millimeter range, really exciting stuff. We are also doing here in our department. Good. So now, well, coherence versus biomass, because that was really a breakthrough, let's say in the 90s, late 90s, beginning of this millennium, to use coherence to estimate biomass. Now, first, let's understand a little bit, this one, this is C-band. Let's just focus on this one here, L-band coherence. So here, obviously, two L-band images, and you see 5th of February, 22nd of March, because it's the Japanese satellite having a repeat pass here of 32, 33 days now, the pulsar system. Yeah, so it's a whole month is between the two images. But what we want to map, or what L-band maps, is anyways the trunks and the trees that do not move. Okay, here we have our stem volume, cubic meters per hectare from the forest inventory. And this is just plotting against it the coherence. And remember, before we saw on the y-axis the sigma naught, the dB. And what happened? We had an increase of sigma, increase, and then at a certain point, the saturation. So with coherence, this looks better than it is, because we also have a kind of saturation. We have the opposite relation. We have zero coherence, or very low coherence. Where it is here, sorry, here we have very low coherence where we have very high biomass. Before we had high backscatter where we have high biomass. And we have, of course, here very high coherence where we have low volume, no or low volume. Because the amount of scatterers is, of course, increasing with the amount of biomass. And so the coherence, the correlation coefficient, here you see the values 0, up to the highest is about 0.7, is of course decreasing. So we have now another way to describe. And okay, well, this is Yeah, not so. It's just for C-band, another example. Okay. Where are we going here? Yeah, strength of multi-temporal data. Again, yeah. So this is not next to each other. Remember the earlier graph that I showed you was 9 JERS backscatter images related or used to retrieve stem volume versus the ground truth stem volume. Yeah, I can go back again. It's that far away. Yeah. Here we had 9 JERS L-band images that have been used in a water cloud model to retrieve stem volume, and this was the relation to the in situ data, so the forest inventory. Looks good. Let's see where it goes up to 150 cubic meters per hectare. Root mean square error, 33 cubic meters and 22%. Okay, now we go forward to our C-band coherence. That is. So these are now 9 coherence maps, yeah, which means that I'm not sure whether it was 18, either we have 18 amplitude images that were used to produce, because we need pairs to produce the coherence images, but you can also produce coherence. We do that now with our Sentinel-1 time series. Yeah, date 1 and date 2 is the first pair. Then the second pair is date 2 and date 3. And then the next pair is date 3 and date 4. And so you move through the time series. That's also it's a good way to get many coherence maps. But yeah, looking here, or we even have a 300 cubic meters per hectare term here in this image analysis. But you see, well, what is it now? 10 cubic meters per hectare and only 7% error. So, and remember these 3 little images with which we started this morning. Yeah, where it also visually already became obvious that the coherence, although based on C-band, had a clearer distinction of forest non-forest than the L-band backscatter image. And this is what is being reflected here. The error goes down because the coherence for this territory, Siberian boreal taiga forest, the regression power of the C-band coherence signal is bigger than the L-band backscatter amplitude here in this example. That can be debated. Yeah, it's here we had optimal conditions. These were winter acquisitions, actually, from which the coherence was calculated. So, and I think the JERS was not from winter. So there's always these environmental aspects to consider. But let's just stay with the, I don't want to say it's better, I just said it's better, but it is, the C-band coherence is comparable to L-band intensity results. Okay. But let's have I think I don't have the time for a break, but let's break in that sense. Is there any question at this point that you wanted to ask? Perhaps. So I see those people who I see, they're smiling. Okay, that's good. Then, yeah, sorry, let's rush further the next 30 minutes. So what is this? The forest height, going through forest height. I mean, this is, of course, today having the wonderful JEDI system up on the International Space Station, and there's data already being made available. Yeah, you can also retrieve biomass using the LiDAR results, but of course this is not fully coverage. It's only along profiles and then it's point samples. But But if you go onto that CCI biomass webpage and look into how the processing procedure to produce a global biomass map has been developed, there is always also LiDAR included as part of the model. So where you have LiDAR data available or from the forest inventory, you would obviously have your own airborne LiDAR data possibly that you can also include. Yeah, this refers to measurements going to forest height. And I mean, obviously, yeah, and this is also something, here you see the surface model, which is obviously something else than the terrain model. You can retrieve that from airborne LiDAR, but you can also get a surface model, for example, from Tandem X. Again, this is principally these two German X-band satellites, TerraSAR X and Tandem X, fly to produce a global digital terrain model. But since X-band does not penetrate the forest, it gives you the forest height with a certain error. But the products are also freely available now, and I'm not sure what the final resolution of the free product is, whether it's 90 or 30 meters, because there is a 10-meter terrain model. So I'm not sure that we would have to look up, but they use such sources. This X-band surface model is, of course, a very nice, again, and very nice input to train any biomass algorithm to compare to that acquisition when the Tandem data was acquired. Okay, yeah, this is biomass retrievals from LiDAR and then compared to P-band. This is from a P-band airborne campaign. Let's see what else we have. We have also the CLP and the X-band here. So here this is a profile over a territory with forest canopy. So you see in green and black the first and last returns, which gives you the forest height actually. But here you see very nicely how the blue and this pink line C and X-band. Now there are some areas where they quite differ, which shows the difference of the X and C band penetration depth into the forest. But then there are other areas where they nicely, even with the L band here, coincide. So such differences, of course, are being caused by the density, by the geometry of the forest at that point. And so this could be another nice application of, again, with the C-band sentinel data, you can, from the interferometric pair, you can produce such a surface model. And because if you would apply interferometry to produce from Sentinel-1 a DTM, you would think you want to produce a terrestrial model. Yeah, don't forget. Also, the C-band signal comes from the top of the canopy. So if you produce a surface model, you are indeed producing a surface and not a terrestrial model. And this is a very nice example showing the difference of now what is the real forest height, the first LiDAR return from the top, what is the ground, and the P-band, of course, this is what we want. The P-band gives us reflections from the ground, so it's similar to the last return of the LiDAR. And X and C-band, I'm a bit surprised about the L-band results here. I would think they are much lower. A publication from Woodhouse, who also has some great teaching material in the internet. Yeah, I don't want to go into the POL-INSA results very much because that's let's say radar science having airborne acquisitions. But perhaps if you are interested, then there's further graphs here because I want to get some more applications. So especially DLR, the German space agency located in Oberpfaffenhofen, a very small town west of Munich. They have this fabulous airborne SAR system with which they can do all kinds of things. Here, this is PolInSAR, polarimetric, interferometry, or even the tomography. And so these results come from these airborne campaigns. But again, this is just showing what is possible with radar, but this is really special, very special interests. But principally what you see here is, of course, that any model, whether it's just a simple regression model, or you put in some estimates like that water cloud model, you always need the reference, the in situ data with which you then are able, based on the regression, to invert from SAR measurements to forest parameters coming from training in the forward model. Just a second, going to the there's lots of information. I mean, it was in any ways too many slides for not just short 3 hours. So, but there's lots of stuff you can look up in the meantime and just see where this goes versus the modeling of a single estimate, and then the more data you add, the better gets the regression. And that was another finding from the beginning of this millennia. Maurizio Santoro is a postdoc also from my department, also excellent radar expert, and also has worked extensively with us in the projects jointly with Russia, especially Siberia. And here, that was a project called Biomass for biomass measuring with the NVSAT ASAR system. And ASAR was the first time where we had a glimpse into the possibilities using multi-temporal or perhaps even hypertemporal images. So here you see that of course the model retrieval. So, and that is another message to you. How do they say that a take-home message for you? Yeah, that it is absolutely surprising how adding up images through the time series helps to explore the surface geometries. So even with the C-band, you remember those first graphs on where C-band comes from, or well, they didn't model the tree, but because it's a mixture. But the more data you add, the more this full wealth of backscattering geometries becomes visible. The clearer is the connection between the scattering center or the scattering origin, and the surface structural surface phenomena that you want to retrieve. So that is the basis why the retrieval gets better and better the more images you add. And actually even independently from the environmental effects. If you now here it's just one regression you do to an inventory term, the growing stock volume. And here's the comparison of the inventory map, of course, based on in situ and then extrapolated from in situ measurements, and the resulting biomass map from 92, in that case, ASAR, NVSAT ASAR images. It doesn't look too bad. And it's, of course, I mean, much more effortless. So why I'm saying independently from environmental effects, we did some analysis now. We just drew actually 4 or 5 years of Sentinel data into a K-means clustering, because we were interested in grassland in South Africa, in grassland communities. And of course, yeah, you will see where you have drastic effects like a fire or logging, where you have drastic changes. And there are multi-temporal analysis models like BFAST, breakpoint analysis, when you analyze the time series. But we said, let's just throw everything together and see whether we can, exploring the whole time series, detect different geometries in that grassland cover. And we got surprisingly good segments. And of course, then you have to start asking what may be influenced by abrupt or breakpoints, but you can compare that. That's not a big deal. So you can identify, is it really that plane community that I'm mapping, or is it a change on the surface? So also here, this was putting in images from summer and winter terms. And of course, yeah, there are some features that may be related to other environmental aspects. Examples. Okay, we have 20 minutes and we have 5 projects. Good old Siberia project, then an extension to China, then a first pan-boreal growing stock, an example from Kruger National Park in South Africa, and I think probably the last one I will skip. It's another of these airborne examples, but you have the slides anyways. Okay, that's of course my favorite topic. It's so old, but it's still gives some of the important messages. The Siberia Project was my first cooperation project with Rosles from Krasnoyarsk and from Irkutsk, and many nice friendships built up based on this. And what is even nicer, Siberia is not only the location. We are looking here at a region north of Krasnoyarsk, but it's also an abbreviation. It stands for SAR Interferometry, SAR Imaging for Boreal Ecology and Radar Interferometry Applications. It was just really nice that abbreviation we came up with, the SAR Imaging for Boreal Ecology and Radar Interferometry Applications. And it was really indeed the first time that for a large area, SAR coherence was evaluated. Again, here you see a similar thing what we saw before, coherence, gamma, decreasing with growing stock volume, increasing the cubic meters per hectare. And here we see the same problem, the saturation somewhere here at 100, let's say 100 cubic meters per hectare. Yeah? So we cannot distinguish denser forests. But this is only one interferometric pair, so it's only one coherence map, not 9 like we saw before. And this is a color composite of actually the same type of 3 images, what we've seen before, in red, and this gives a lot of information. In red is the coherence from one single interferometric pair, showing clearly, and here you see the polygons of the Russian forest inventory, clearly see the clear cuts, very nicely, no problem, as we've seen before on the black and white. Then green is the JERS intensity, so the backscatter amplitude, and blue is an ERS intensity, where we saw, well, it's not much in the ERS amplitude. And these are all only single images, but you see, putting them together in a color composite looks almost like a Landsat image. Yeah, it still has a speckle, we know that's a problem. But then it's not filtered. There's nothing was done to this color composite, just putting the 3 products together. But yeah, looking in the forest, you see also there are differences coming up with greenish, bluish, a bit more yellowish. So in the L-band intensity and the ERS, the C-band coherence is really a lot of information. Okay, and that was then explored. We just put them, what I just said, we put them together, the L-band intensity for the whole image versus ERS coherence. Yeah, and then you get some funny scattergrams. And what is behind the scattergram is down here is, if we wanted to classify the images, down here is the water. Water has a low coherence, as we learned, and it has low J sigma naught, low L-band backscatter because specular reflection for L-band mostly is water very smooth. But here in this thing here, we of course, this is continuous information. So putting classes into such a continuous information cloud, let's say, is always a problem, because where do you put a threshold in this here? It's actually would have been better to have continuous, but in that case, our Russian colleagues wanted to have classes of biomass classes. So what's behind here is mature, medium, clear cut, and then here, and of course, this kind of feature in your scattergram depends on the image contents. There may be water in it or not. This was a scene with water in it. And smooth fields, they come up here. So the smooth fields, what is it? High coherence and relatively low L-band backscatter, because a smooth field will cause specular reflection. And this could be, like those white areas in the 3 images we saw before, a smooth field, high coherence and low backscatter. Okay, so having this, and again, this was in the late 90s, having only one L-band image, having only these 2 C-band images, from which we could produce, again, one coherence map, so really very restricted information. We applied the same concept as with the water cloud model to this. So saying, okay, what we need is, what we're looking for is this growing stock volume. Okay, what we need is we have to start somewhere at coherence at 0 cubic meters per hectare. So this is why we have to know what pixels are from pure ground. And then we need to have somewhere where we say, okay, here 75% of the maximum value is reached. Somewhere where is the largest? Where do we define is the largest growing stock volume that we can distinguish? So that is how that really simple semi-empiric regression model has been defined. And then the next step was also to identify biomass classes. And again, they are all overlapping, which is a problem if you do distinct classes. Continuous classes are, I think, mostly always better when you look at natural landscapes. So here we had 4 classes, 0 to 20 cubic meters, 20 to 50, 50 to 80, and then above 80. That was we said, okay, above 80 cubic meters per hectare, we cannot really distinguish. We run into the saturation in the coherence, but also in the L-band backscatter. So, okay, use the model to calculate the class means, then apply a maximum likelihood classifier, as I just said. And at the end, we also did a little filtering, so make it a bit nicer. And that was the classification chain to come up in the year 99 with a very large area biomass map. That was the very first biomass map from radar remote sensing. Here's the Lake Baikal, here's the Yenisei, Krasnoyarsk must be around here. And flying to the north, this is here Bratsk Dam and then Angara. So the resolution, so this is just, this map actually covered a wall like 3 meters high, 5 meters wide, and about 100 maps, each a scale of 1 to 100,000. So do I have it on the next slide? This is looking into the map. This would be the color composite again that we just saw. And this would be, I will tell you about the black spots. This is the respective, so here you see a pipeline running through, and it's kind of also captured in the model. You see the densest forests. Here you see also some logging that is represented here. Well, here areas like this could be fields, but there's other areas like this could be fires, or here this could be also a result of a fire. But now you have a biomass map that can help you also. This is for year 97 as a reference, and then to observe changes. But of course, now we are at a different point of also developing the model, because one big issue was in the year 1997, 98, 99, the only elevation model we had available to correct for radiometric effects that we discussed yesterday. We said any slope steeper than 15%, 15%, any slope steeper than 15%, we will mask out, because we are not sure that our model, so all the assumptions on backscatter intensity and coherence are correct. So we just mask it out. So this is what these masks is, and the only elevation model that was available was the G-Topo 30. So an elevation model based also on an altimeter, I think it was an altimeter on a satellite, and giving us a resolution, I think it was 30, half a degree, 500 meters. Yeah, 500 meters. So that's a very coarse elevation model. Now, in the year 2000, the shuttle radar topography mission took place. SRTM data is available, even 30-meter resolution. Yeah, so this mask would look very different, and we have other radiometric models. So we should actually redo this. And now and then I think about it, but we need staff, obviously, to do that. The data is all available, and it would be a wonderful exercise to produce with a much better quality a biomass map, reference map for the year 97. Okay, but the most important part is that, so these were over 100 scenes, 120 ERS scenes, about 100 ERS and 120 JERS, because JERS was a smaller frame. But what is important, this regression model was adapted frame by frame by frame. So this method was automatic, adaptive, as I just said. It was consistent. It was based on the regression of the L-band backscatter and the C-band coherence. And it was validated actually independently. We took out some of the in situ data for independent validation through our forest friends in Irkutsk and in Krasnoyarsk. And for these validation sites, the accuracies for the 4 classes, it was only 4 classes, was about 92%, so very high accuracies. Again, data don't lie. Remote sensing data don't lie. Okay. So again, an old project over 20 years ago, but all the lessons we took, they're obviously still valid, and they can still be applied. And now we have Sentinel, which is a much better data source. And what we even did is we extended, we had another project, cooperation between European Space Agency and China, and we extended it to map all forests in China. Same method. So this is the basis, the coherence maps. And you see there are gaps here because this coherence map was based on a so-called tandem acquisition period when both satellites ERS-1 and 2 were flown on an exact orbit. And not the whole Earth was covered. For Russia, we had a dedicated campaign, so we had a nice coverage. But for China, there was never such a dedicated campaign. So there are some gaps for this time frame on the mid-90s. So there's not such a reference existing from radar. But what I wanted to tell you here, and this is also what is done now much nicer in the CCI Biomass project. We didn't have in situ data here for the area, so we helped us by looking into an optical product, the VCF tree cover, Vegetation Continuous Field. It's a product from the University of Maryland. It was developed on NOAA AVHR data and then applied to Landsat data. And yeah, it's a very nice product that tells you per pixel the percentage of trees and bushes and grassland from optical time series. But what we needed is, we wanted to know where is no tree cover. So here VCF 0, because that indicated to us, okay, and it proved to us the highest coherence values. And we took this for our model. That's the area we define as ground. And then the highest biomass or the highest tree densities, the highest amount of tree cover. And for this, we use the VCF. And again, looking at our coherence values, there we saw, okay, this coincides with the lowest coherence. VCF stops at, what is it? I think it's 75 or 85% tree cover, because with the optical data, they cannot resolve further. But for us, this was enough. But what was also very nice, and it would be worth several PhDs to go into this further, yeah, this almost linear regression between the optical product, VCF tree cover, and the just for a single pair, single coherence map, how it coincides. Yeah, but obviously there is information in here where we see an increase of tree cover. Coherence is not reacting yet, but then it suddenly reacts. And we don't know what would happen further here, what the sensitivity is, because the VCF tree cover stops there. Yeah, so with that, we produced here these two stem volume maps for the northeastern territory and whole southern territory, which again was a surprise, seeing our 5 classes or 4 classes, that even here for the subtropical regions, the coherence, again, the model is based on L-band backscatter, and C-band coherence works very nice in just a single date, so we are in a much better condition. So and these were the 3 maps developed at the beginning of this millennium, and quite a breakthrough to large area mapping. Okay. And then of course, and that's all a different discussion on change. Having biomass maps for different periods, they are based on different data. So here for the 90s, AS12, then for this millennium, the SAR. So, well, the nice thing is if you know what the error margins of your model are, you produce the map, you produce the biomass map, and then you start comparing biomass map. Because if you start comparing satellite data, things get very complicated. Well, if you're comparing map products and you carry the error with you, but on the other hand, well, you know the problems in either map, and thus it is easier to compare map products to produce a change. Okay, so here we had some examples, and now coming up to increase and decrease of biomass. Here regrowing, there was a very large forest fire in the upper northeast of China. This was regrowth, regrowth. When we drove through that area, it was just impressive, kilometers over kilometers of planted new forest. Very large efforts, and China is famous for their regrowing activities. And here another example of a forest fire that, well, in this case, we could only validate it with looking at Google Earth. So this was now for the northeastern territory, such a change map. But again, also an old product, but comparing 10 years of, not 10 years, but a time difference of 10 years of 2 biomass maps. Yeah, and I think, this is where we have to go now with the recent satellite data that we have, produce the best possible biomass maps, and then we have to see how do we go back in past if we want to contribute substantially to climate change. Then obviously we have to produce earlier historical maps, discuss their errors, and go into change predictions. Yeah, I rushed through this because this is maybe for you not so relevant, but it was also one of the prerequisites to start with a global attempt. This is this Biomass growing stock volume product. We had 3 sites: Quebec, Sweden, and Central Siberia. This is the map, going up now to 500 cubic meters per hectare, but this has a less geometric resolution. It's only 1 kilometer. Yes, we again with Baikal, Angara, and Yenisei, Krasnoyarsk here, and Dobana plateau up here. But again, yeah, it shows you spatial, very spatially interesting information. But this map was based on a monitoring mode from ASA on a 1 kilometer, like NOAA AVHR, that is not existing anymore. But it would have been a nice way to produce also, again, similar to NOAA, AVHR and individual time series, produce a 1 kilometer product from radar. Yeah. So from this were first continental maps, but also the same thing for Mexico. And this is based on, well, now we are in the tropics and subtropics, but again, this map was based on so-called hypertemporal data that I should have said here. We used the global monitoring because we had several hundreds of acquisition in this time frame, 2005 to 6. And so that's the other take-home message. But again, as I said before, yeah, adding up different times helps a lot in the retrieval. And here we were very surprised to come up to 500 cubic meters with a C-band sensor, just because of the time series. And now I do have to finish, but I would like to finish this with another example from South Africa. Again, older data from a shuttle campaign in '94. I mentioned that, I think, in the first on Monday, where we had simultaneous C-band and L-band data acquisitions, and they were actually polarimetric. And now applying this, it's called a decomposition model based on this C-band polarimetric and L-band polarimetric data. So having HH, VV, and the two cross polarizations, we developed a woody cover map, which is important in savanna systems. And this comparison, what it shows to you is the different sensitivity based on the wavelength. Yeah, so here on the left side, on the left, we have the L-band data, which shows for much larger territories a low woody cover, but obviously because the woody cover the L-band can detect, there has to be of quite some size before it would map a woody cover pixel. Now, with the same method, but applying the C-band data, you see how this low biomass or no woody cover classes disappear, and it's much more sensitive to different grassland types. So here the message is, well, it's obvious that different wavelengths see different structural components on the lens surface. And this is, we have L-band data, we have C-band data, we have X-band data in space. So we should much more start thinking in geometries when we explore these different wavelengths. And we cannot tell, this was a result of a master thesis. And we cannot call these products woody cover because this C-band woody cover is a different woody cover than the woody cover map by L-band. So we have to think in these geometries and relations, and this is of course very, very exciting and a different approach to remote sensing. Okay, yeah, this is now, why is this again? I'm a bit surprised. I'm jumping quick on from South Africa again to Siberia, actually. But there's a similar things we saw before, so there is nothing new in this one, except that this water cloud model was then extended to interferometry, and there's also lots of publications on this. And this is, of course, now nice that we are not only looking at sigma naught, ground and forest, we are also including now gamma, the coherence. We also train a model on what is the gamma from ground and what's gamma from vegetation. And we extend these extinction factors with referring to attenuation gaps between the trees and geometry of the interferometric system. So we can come up with an extended empirical relationship Yeah, and this was one of the very nice results here from the Irkutsk region, now based on ALOS pulsar on L-band coherence. Okay, yeah, that was an L-band coherence. If you have the data, it's very nice. If you look in, there's lots of detail now on also the variation of the biomass in the remaining intact forests, and you even see the piles after the lumbing here. So again, a lot of I think very worthwhile information coming from the Japanese L-band satellite. And again, starting next year, you will have free data from the NASA ISRO NISAR mission. Okay, yeah, no, I thought, Savannah, there was more on the Kruger National Park, but the message, I think you got the message from the two images about the relation of retrieval model and in that case, woody cover parameter. And this one, I just rushed through whether there's anything important. I mean, there's of course lots of important stuff, but again, this is based on airborne campaigns, a lot of radar science really in this here. And unfortunately, you have and can read through this, and then there's this summary coming that lots of pros and cons and some literature, but it's of course also extending and more references. Okay, yeah, I'm glad. Sorry, I rushed you through the last slides, but you have everything available that you can look up. And with this, well, I hope you enjoy your practicals again this afternoon. And then I see you again tomorrow morning. Have a good day to Krasnoyarsk and to Moscow. Bye.
Goodbye.